Bernoulli's principle is a physical principle formulated that states as the speed of a moving fluid increases, the pressure within the fluid decreases. Bernoulli's principle is named after the Swiss scientist Daniel Bernoulli. The principle states that for an inviscid flow, an increase in the speed of the fluid occurs simultaneously with a decrease in pressure or a decrease in the fluid's potential energy. Bernoulli's principle can be derived from the principle of conservation of energy. It can be demonstrated by the Bernoulli equation, which is an approximate relation between pressure, velocity, and elevation. As a fluid passes through a pipe that narrows or widens, the velocity and pressure of the fluid vary. As the pipe narrows, the fluid flows more quickly. Bernoulli's principle tells that as the fluid flows more quickly through narrow section, the pressure actually decreases rather than increases. Bernoulli principle can be explained in terms of the law of conservation of energy. As a fluid moves from a wider pipe into a narrower pipe or a constriction, a corresponding volume must move a greater distance forward in the narrower pipe and thus have a greater speed. However, Bernoulli's principle can only be applied under certain conditions. The condition to which Bernoulli's equation applies are the fluid must be frictionless, also known as inviscid, and of constant density. By that mean, the flow must be steady, continuous, incompressible, non-viscous fluid flow. The total energy or a total head remains constant at all the sections along the fluid flow provided there is no loss or addition of energy.
For the theory of this experiment, consider a fluid in the tank that is exposed to the atmosphere escaping through an orifice at a vertical H depth from the free surface of the fluid, point 2 as in figure 1. Following energy conservation, the total energy at point 1 is equal to the total energy at point 2, which can be expressed by the Bernoulli equation given as consider fluid in a tank that is exposed to an atmosphere that exits from an orifice at a vertical h distance from the free surface of the fluid, point 2, as seen in figure 1. In other words, the equation predicts the velocity v of the jet to be equal to the square root of 2gh. It is very difficult to calculate the velocity of the jet. However, it can be measured indirectly by tabulating the height of the water, h, against the time elapsed. The rate at which h change is proportional to the velocity v at which the water exits the orifice, and states that this velocity is not constant. Hence, the rate of h change is proportional to the velocity given as
Okay, in order to perform this Bernoulli's theorem experiment, we have to figure out the objective of this experiment first. The first objective is to determine the jet velocity as well as volumetric flow rate of fluid exiting the orifice of a water tank in the beginning of the experiment. The second is to determine the coefficient of contraction that is available in the system. To start the experiments, this is the apparatus that we can use, that we will be used. Is first water bottle that have even cross-sectional area and clear transparent surface. As you can see, this water bottle have a little bit hole here to let the water flow out, and I have a meter ruler to what we call as to measure the length between the hole and the water flowing out, the length. And next we have food coloring. No, this food coloring is nothing much help. It just to show that the water level that will be dropping out. Okay, and now we will start the experiment. Okay, to start the experiment, we have a really good amount of water, and we are not really just pouring it like carelessly. We have marked a specific height within this hole and the water level, which is this is 5 cm, 10 cm, and 15 centimeter. First of all, we need to pour this water inside of this empty container that have the hole here. So in order to pour the water, we need to cover this hole first to make sure the water didn't just blankly pouring out. Okay, this is for 15 centimeter water level. Before you start to release your finger, make sure to start, this is the precaution to start the stopwatch first. And then take the meter ruler and start to count the line between these holes. So it is 8.5 centimeter. Stop. Okay, now it took 2 minutes and 10 seconds for the water to stop pouring out from the time lapse.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurumizah Nadia Muhammad Harum, and I will explain about calculation for experiment Bernoulli theorem demonstration experiment. Okay, for this experiment, additional data and sample calculation was taken from Bernoulli theorem demonstration experiment for understanding purposes and to support the calculation. Okay, there are 4 things that we need to find and calculate, which are first we need to find beta from the plotted graph, and then we need to find jet velocity of both orifice, and we need to find volumetric flow rate of fluid existing the orifice of water tank. And next, we need to find coefficient of contraction, CC, for both of the orifice. The first thing that we need to find for beta of the plotted graph is gradient, which represent beta squared times g/2. Okay, for orifice with diameter 0.25 centimeter, we will get gradient negative 0.02222. Okay, from there, we calculate the beta from the formula beta squared times gravity over 2, and we will get beta with value negative 2.127 times 10 to the power of negative 3. Next, we calculate beta for orifice with diameter 0.5 centimeter. Okay, from the graph, the gradient for 0.5 centimeter orifice is negative 0.125 centimeter per second. Okay, from there, we calculate the beta, which equals to negative 0.01596. Okay, next we need to calculate jet velocity of both orifice, and for orifice with diameter 0.25, first we need to get the gradient of the graph height of water versus time for diameter 0.25 centimeter, and the gradient is negative 2.105 meter per second. And from there, we will get the V actual, which equal to 0.99 meter per second. Okay, for calculation of jet velocity for orifice with diameter 0.5 centimeter, we need to find gradient for the graph height of water versus T versus time for diameter 0.5 centimeter, and the gradient is negative negative 0.5 centimeter per second. And from there, we will get V actual, which equal to 0.31 meter per second. Okay, for the third calculation is we need to find volumetric flow rate of fluid exiting the orifice of water tank in the beginning of the experiment for both of the orifice. Okay, for orifice with diameter 0.25 centimeter, the Q actual is equal to negative 1.03 times 10 to the power of negative 8 meter cube per second. And for diameter 0.5 centimeter, the Q actual is equal to negative 9.71 times 10 to the power of negative 8 meter cube per second. And for both of the diameter of orifice have the same Q theoretical, which equal to 2.74 times 10 to the power of negative 5 meter cube per second. Okay, next is calculation of coefficient of contraction CC. The first step that we need to find to calculate CC is we need to find cross-sectional area of the tank. So for orifice with diameter 0.25 centimeter, the cross-sectional area of the tank is 4.9 times 10 to the power of negative 6 meter cube. Okay, from the information from cross-sectional area of the tank and information from the beta of the graph, we can calculate cross-sectional area of vena contracta with the formulation beta equal to cross-sectional area of vena contracta divided by cross-sectional area of tank. So from there, we can get cross-sectional area of vena contracta HC equal to negative 1.0441 times 10 to the power of negative 8 meter cube. Okay. Next, to find CC, we need to calculate area of orifice AO, which equal to pi r squared. So, AO for diameter 0.25 centimeter is 1.9635 times 10 to the power of negative 5 meter cube. And from there, from the information area of the vena contracta, from the area of orifice, we can calculate coefficient of contraction CC. So from there, the CC is equal to negative 5.3175 times 10 to the power of negative 4. So to find coefficient of contraction CC for orifice with diameter 0.5 centimeter, the same step of calculation will be applied. So first, we need to find cross-sectional area of the tank with using formula pi times r squared, which equal to 1.9635 times 10 to the power of negative 5 meter cube. And from the information cross-sectional area of the tank and information of the beta, we can find cross-sectional area of vena contracta, which equal to negative 3.1337 times 10 to the power of negative 7 meter cube. And then from there, we can find area of orifice AO with formula pi r squared, which equal to 1.9635 times 10 to the power of negative 5 meter cube. So with the information area of the orifice and area of the vena contracta, we can find coefficient of contraction, which equal to negative 0.016. That's all from me. Thank you.
In discussion, the experiment was conducted to investigate the volumetric flow rate of the fluid leaving the orifice of water tank and also to calculate the jet velocity of the water too. The experiment also performed to calculate the coefficient of contraction which is available in the system. In this experiment, we found that the flow energy is directly proportional to the kinetic energy with time. This is because flow energy basically is work done by pressure forces on the fluid element, and this work must result in a change in kinetic energy of the element. In conclusion, the jet velocity and the volumetric flow rate of the fluid leaving the orifice of the water tank is relative. Thus, coefficient of the contraction is calculated. From this, we can deduce that flow energy is directly proportional to the kinetic energy with time and increase the coefficient of contraction leads to increase of velocity of the flow. Reused water is highly recommended to maintain sustainability in order to avoid water wastage.